that rocket goes to some foreign planet and then comes back. And beta is, we'll just say 0.9, and he ages 1 month. And I made the claim that the rocket is the proper time, and the twin left on Earth will age more. But now let's look at it from the rocket's point of view. From the rocket's point of view, the rocket's not going anywhere. It's the Earth that travels away and then comes back. So from one point of view, it looks like that the person on the, well, actually, this person is still going to age a month. That doesn't change. But from this point of view, it looks like the person on Earth would age 1 over 2.294. That one, he would age more than let's actually give pronouns to it. Lou and Sue. He ages 1 month, and Sue would age less from a different point of view. But there's fundamentally a difference in these two situations here. And that is why that, I'm not going to get into the nitty-gritty math of it, but that is why there is a difference in these two situations, and only one of them is actually true. This is the true scenario where Sue ate. Nope. This is it. It was never written. This is the true one. This is the false one. Where delta T Sue would be 1 over 2.294. And in this one, delta T Sue is 2.294 months. What is physically different between these two situations? Besides point of view.
The Earth is much larger than the rocket.
You're making an assumption there, but if you're traveling 0.9 times the speed of light, I don't know how big that rocket's going to have to be to support those engines. The size of the planet versus the rocket is actually not an issue. Imagine yourself in the rocket, imagine yourself on Earth. Imagine what's happening at the turnaround point. Here and here.
Can you repeat the question?
All right, so ultimately it is what is physically different between these two situations. Besides point of view. From Earth's point of view, rocket goes out, comes back. From rocket's point of view, Earth goes out and comes back. And so, as hopefully a hint towards what's physically different is, imagine what is happening to Sue on Earth at this point versus Lou in the rocket at that point. In what way?
What's changing?
Okay. Then I would say, yes, it does have something to do with changing direction. So you stay on Earth, your evil twin gets in the rocket, goes to a distant planet, and comes back. Will you know when this point happens?
No.
You're in the rocket, and you shoot over here. Will you know when this point happens?
Yes.
Why?
Because you can see your path that you've been in one.
You're seeing a ballpark. Think physically. What do the Earth people feel at this point, and what do the rocket people feel at that point?
Inertia,
In what sense?
like the momentum is changing,
Okay, and what would cause the momentum to change?
changing direction.
What would cause momentum to change? As in, if you have a certain momentum, what would cause that to change?
Speed.
Pardon?
The speed. Speed.
Speed. All right. Speed and direction and mass are the three things involved in momentum. I'm talking about change in momentum. What is oh, that's right. I was expecting you, because we just talked about it, but that was the other class, we just talked about it. Impulse. When someone suddenly buys you flowers. Okay, at least I got one nod of recognition. What is impulse? Besides change in momentum? Apparently made a huge impact when we went over it the first 8 weeks. Force times time. In order to change momentum, a force needs to be applied for some amount of time. For the rocket to turn around, a force has to be applied to the rocket. When the Earth turns around here, no force is being applied to the Earth. That is physically a difference in these two situations here. When the rocket decelerates and then accelerates again, we are jumping out of special relativity for a moment, and then we come back into it. Because special relativity assumes constant acceleration. The Earth's not accelerating here, only looks like it's accelerating here. But the rocket is accelerating at that turnaround point. So there's physically a difference with this. And so, as a general rule of thumb, if you want to figure out what's the proper frame and what's the not proper frame, think about if some object is zipping by really fast, that's going to be the proper frame. Whatever time happens in that, so if I'm on Earth and I see something zipping by from their point, well, actually, that somewhat misleading statement. If I have two objects that start together and they end together, do it that way, the one that was physically going to basically change directions, that's going to be the proper frame. And I'm just going to sort of leave it at that as opposed to go into any detail about why that's the case. So we have this T is equal to T gamma. All right. Let's add to it. This is known as time dilation. So you're on the rocket ship again, and you're going to some distant planet X. Got Earth here, and the rocket goes, from Earth's point of view, rocket goes to the distant planet, it sees it, and then comes back. Let's take a look at the distance traveled. So let's do this distance here is initially L sub, I'll just do L sub E. So the distance from Earth to planet X is E. Yeah, I made too much of a generalization just a moment ago. But we'll get there. All right, so how far does the person in the rocket travel? Well, I know that speed is distance times time, or sorry, divided by time. So the distance should just be the speed times time. And so from the Earth's point of view, the rocket is going to be traveling, well, 0.9, or do it this way. We'll be traveling at some value beta c, that's how fast it's traveling, for a certain amount of time. From the rocket's point of view, well, actually, from the rocket's point of view, how far does he actually travel? Twice the distance? No. Pardon? How far do the rocket people say they actually went?
Only how long it took to get to X.
How fast are you moving right now?
How fast the Earth is moving?
Let's assume the Earth is still. So how fast are you moving right now?
0 meters per second.
Really? Doesn't look like that to me. How can you be so audacious as to claim you are not moving and everyone else is? From the rocket's point of view, how fast is the rocket going?
Zero meters per second.
Therefore, how far does the rocket travel from the rocket's point of view?
0 meters.
Yeah. From the rocket's point of view, what's actually moving?
Earth.
And,
The distant planet.
yeah, planet X. So from the rocket's point of view, this is actually moving towards it. So from the rocket's point of view, how far does this actually travel? From the Earth's point of view, it's traveling that distance, but from the rocket's point of view, well, the rocket's not going anywhere. It's the planet that's moving. Earth's point of view, the planet's not moving. So the length from the rocket's point of view would be how fast the planet's traveling, which would be the same speed that Earth says the rocket's traveling, times that proper time. I'm doing this differently than I've done before, so hopefully I'm not going to screw up something here. So LE divided by time is equal to LR over TP. Actually, do that differently. So LE, no, I'm gonna stick with that. LE over time, so basically I'm isolating beta C is equal to the rocket length over the proper time. So LE is equal to LR T over TP, just multiply both sides by T. And we have, well, that's just 1 over gamma. So that's LR over gamma. So I have gamma times the LE is equal to LR, and let me take a moment, because I think I have something backwards here. Yeah, that's something pretty backwards. All right, different tack. Sorry about that. Sort of scratch through or somehow note that there's something off what we just did. All right, so from this point of view, what's the proper length? Are the people on the rocket measuring the proper length, or the people on Earth measuring the proper length? Pardon?
On the rocket?
So if proper is the standstill measurement, is the distance to the planet basically staying still?
Yes.
I guess from the rocket's point of view. So if you're in the rocket, is the distance to the planet a constant?
And you're looking at, yeah.
You say it is a constant, the distance that the rocket is to the planet? All right, I'm the rocket, you're the distant planet. Is the distance between us a constant from my point of view? All right, so we have Earth right here. As I go towards you from the Earth's point of view, or you come towards me from my point of view, is the distance from here to you a constant? So that's the proper length. So that's L proper. Because we're dealing with, it's all dealing with relative to what? What point of view? So if L proper is equal to how fast we say the rocket is going times the time. So that would be the proper time there, which is somewhat of a contradiction or a downright contradiction of something I said a moment ago, 5 minutes ago. And then from the rocket's point of view, that's how fast the planet X is going times the amount of time. Because the rocket is measuring the time it takes for the planet to come to it, so the planet is not at rest relative to the rocket. And then solving for BC, we get LP over TP, or the distance from the rocket over time. Multiply both sides by t, so we get the proper length times time over the proper time is equal to the length from the rocket's point of view. That's gamma, so we get gamma times the length of p is equal to the length of r. In other words, we have I feel like they got it backwards again. Just one of them. All right, what I'm gonna do here, just so that I don't go back and forth on this, I'm gonna pause this.